All right, folks, welcome back. Let's go ahead and let's get started and let's finish up with this problem here that we started yesterday. It's a bit more challenging. I don't know how well you guys worked it out, but let's go ahead and let's take a look at this problem. Maybe it's a little unfair for me to ask you to do this, but it is what it is. Okay, so let's take a look at this problem. I want to work this out for you. So let's you need to pause the video, go get your the work that you did for this problem, and then let's compare answers. Okay, so go ahead and get it, and let's work this out. All right, so let's go ahead and let's take a look at what we have here. Okay, and I told you when you do these kinematic problems, what you want to be able to do is you want to make sure you identify what you're given first. Okay, identify what you're given, draw your picture, include all that given information, identify what you're going to solve for. Then what you need to be able to do is find the correct kinematic equation in order to solve for your unknown variable. Okay, and in order to identify the correct equation, you look at the equation that has all of the variables that you need included in there, the ones that are given, and the one that you're solving for, and then you plug it in and you solve. Pretty straightforward stuff. Okay, so let's go ahead. Let's start out then, and let's take a look at what we have here. What are we given? Okay, so let's take a look at the first one here. We are told then that we have this first one here. It looks like with the unit here, this is going to be an velocity. Okay, so we have a velocity here. Whether it's initial or final velocity, we'll figure out in just a moment. Okay, we also have a time here. So this is time. We're given a time, and if we take a look at this here, we are given displacement as well. Okay, so we're given time. We're given displacement, we're given velocity, and then we're asked to find then here, we're asked to find initial velocity. So we're trying to find initial velocity. This must then be final velocity. Okay. All right. So we're given final velocity, we're given time, we're given displacement, and we're given initial velocity. Okay, so let's go ahead. So we're solving for initial velocity. Okay. Let's take a look at the kinematic equations that we're given. Okay. All right, so the first one then was V final. And again, make sure then, I'd suggest you probably memorize these here. If you don't have them memorized right now, that's okay. Just have these equations on a card, or make sure you have it somewhere you can refer to. All right, so our first equation there is for V final. Okay, so we also had an equation which gave us constant velocity times time plus 1/2 acceleration times time squared. And then for the last one, then we had then V final squared is equal to V initial squared plus 2A delta X. Okay. All right. So let's go ahead. Let's take a look at this here. We want to solve for V initial. We have V initial in this first equation here. Okay. And so with that said, then we have V final, which is good. We have V final right here. We have time, which is given to us right here, but we don't have acceleration. So right now, then, this equation doesn't work for us, folks, because we have two unknown variables. Okay, let's go to the next one. All right, so this one here, we don't have the initial, though. With that said, we could assume, if we wanted to, we could assume then that this V initial here, this velocity here is a constant velocity before it started the acceleration. So there it is. We have initial, so we can assume that that would be V initial if, again, the bike rider was initially riding at a constant velocity and then started to accelerate. Okay, that's the assumption we're going to make here. Okay. All right. So with that said, do we have delta X? Yes, we do. Do we have, and there's V initial. Do we have time? Yes, we do. But we don't have acceleration. So we can't use that either. Okay. And so let's take a look at this last one here, folks. And if you take a look at this one, we have V final. Here it is, V initial also. But again, you're going to see that the issue that we're going to have here is that we don't have acceleration, and we don't have acceleration for any of these. Acceleration is not given to us. If you look at this problem here, folks, all they tell us about acceleration is that the acceleration is constant, and they tell us that without giving us a number. So how are we supposed to plug it in order to solve for this problem? And that is the question that I think may have frustrated a few of you yesterday. Maybe it didn't. Okay. But to answer this, but we still have to answer the question. We still have to be able to solve for it. Okay. And so if you notice this one, if you notice in this particular problem, no one equation is going to get us the answer. So in this particular problem here, we actually have to combine together two of these kinematic equations to derive an equation, to derive a brand new kinematic equation that's not given to us here, that will allow us to solve for this problem. Okay. And that's what you had to do. And remember, I had mentioned then that when you move on, you're going to see then that for about half of you, when you move on to physics, you're going to see then that this is what you're going to have to do. What we've done so far is pretty straightforward. But in this particular problem, again, it's a little bit unfair, but I think you folks are up to the challenge. This problem's a little, but in this problem, you have to do that. Okay, so let's go ahead then and let's work this problem out. Okay, so there it is. That's the issue that we have. That's the problem that we have. Let's go ahead then and let's, again, like I pointed out to you, drawing a picture is very helpful for these types of problems. Okay, so there's our bike rider, okay, mass M. The bike rider is moving in the positive x direction. So let's go ahead and write this down as the positive x direction along the x-axis. This must be then the negative x direction. Okay. All right. So we read this problem here then. We are told then that the bike rider pedals at a constant acceleration, reaches a velocity of 7.5 meters per second over 4.5 meter per second, 4.5 second time interval, during which time he or she covers 19 meters. What is the biker's initial velocity? Okay, so we can imagine then that at some point here, and I'm just going to write this here. I'm going to draw this as a dash line. Okay, at some point in the motion of the bike rider here, the bike rider starts to accelerate. So this interval here of time, okay, this interval here is the interval of acceleration, and we're looking at this interval here, which is, and the information we're given involves this interval here, and we're trying to figure out what happens before he gets to this time interval. Okay, and so let's go ahead and include the information that we're given. So we were told then that at the end of this acceleration interval here, so he accelerates for this interval here, at the end of that, okay, he gets to a velocity of 7.5 meters per second. Okay, now we were told then during this interval, during this acceleration, it takes him, he accelerates for 4.5 seconds. So the acceleration interval lasts for 4.5 seconds, and the acceleration interval also covers a distance of 19 meters. Okay, so that all of this information involves the interval at which he accelerates, which only encompasses this part here. Okay, so this is the interval of the motion that is acceleration. The time refers to the acceleration time. The displacement refers to the acceleration displacement, and the final velocity here is the velocity that is achieved at the end of this acceleration interval. Okay, but the question is asking us then, what was the initial velocity as the biker enters this acceleration interval here? Okay, what is the initial velocity? Can you assume zero? No, you cannot assume zero. That would be too simple. Okay, and furthermore, if you did the math, if you did that, he wouldn't get to 7.5 meters per second if he started out at zero. Okay, you can plug in those numbers. You can plug these numbers into the kinematic equation, and it won't work out for us. Okay, because he doesn't start out at zero. He does not start out at zero, and so we can't assume that. Okay, we have to solve for it. Okay, all right. So let's go ahead and let's write down the kinematic equations that were given to us. Okay, so let's go ahead and write those down really quickly, and then I'm going to show you how the process by which you go about doing this. Okay. All right, so let's go ahead then, and we saw then that the first kinematic equation, V final equal to V initial plus A T. The second one was delta X is equal to V T plus 1/2 A T squared. The third one, V final squared is equal to V initial squared plus 2A delta. Yep. All right. So at this point then, we want to make sure that all three of these have acceleration. We're not given acceleration. So in this problem then, make sure you understand acceleration is not known. We don't have a value for acceleration. All that we know is that the biker accelerates. Okay? All right, so what we want to do here is we want to be able to try to obtain an equation and use it. And again, you can combine together whatever equations you want to, but we're going to try to combine together equations that is in the simplest manner possible that will give us V initial if we know time, displacement, V final, but we don't know acceleration. Okay, all three of these have acceleration. So what I'm going to do then is let's go ahead and do this here. Okay, let's pick this one and that equation. Okay, and what we're going to do then is we're going to substitute. We're going to substitute using. I refrain from using this one because you're going to see that you have some you'll have some issues here with the square and the square here, and then you'll have to use uh, uh, a little bit more algebra than I think most people are used to or comfortable with, especially when you're dealing with squares here, in order to get an equation that you're going to use. Because you have the initial here, and you have v final here. You could use this one, okay? But here, folks, we have v initial, v final here. We don't have acceleration, okay? So we want to be able to use these two equations here to get that. Well, again, here we don't have v final, so you want to make sure that somehow when you combine these two equations together, that you're going to get that. Okay, so let's go ahead then and let's work through that. Okay. What I'm going to do first is I'm going to solve this for acceleration. Okay, I'm going to solve that for acceleration. Make sure you're able to see that. Okay, to solve for acceleration here, then we subtract the initial from both sides and divide that by time. Okay, which is the definition for acceleration. Okay, so the initial times all over time. Okay, all right. So that's what we're going to start out with. Okay, so we need acceleration. What are we going to do with this particular acceleration? Can you imagine then? Can we take this now, this right-hand side, and substitute it in right here? Okay, so let's go ahead and do that substitution. Okay, so therefore then we have delta x going to be equal to vt plus 1/2. And let's substitute all of this in. This is going to be v final minus v initial all over time. And we're going to multiply all that, remember, by t squared. That has to be on the inside, outside. So we took this part here, since this is acceleration and that's acceleration. A's are the same. You can go ahead and we rearrange the first formula to find out what A is. And now then, once we have that, we can take all this and substitute it in for the A right here. And that's what we have at this point. Okay, so hopefully you see that. Now, before we go on, what we want to assume then is that he is moving at constant velocity before he enters into this acceleration phase. Okay, and so this velocity here represents the velocity that he's moving at before he enters there. So that's going to be an initial velocity. So that velocity here, this velocity during, let me go ahead and write that in here. The velocity during this period here, which is going to be no acceleration, okay, is going to be the velocity enters into the acceleration phase. So this will also be the initial velocity. Okay, so that's the initial velocity right there. Okay, all right. We're assuming the time interval is going to be the same. Okay, so with that said, then let's go ahead and now we can go ahead and let's start the let's go ahead and let's start solving for this problem. Okay, all right. So therefore, we have then v initial times time plus. Let's go ahead and hopefully you see here that, and one of those cancels out. So this is going to be 1/2 v final minus v initial all times time on the outside. Okay. All right. So with that said, that's all going to be equal to delta x. Okay. All right. Let's continue on. Delta x then is going to be equal to v initial times time. Okay. Plus, let's distribute everything through. Okay. 1/2 v final times time minus 1/2 v initial times time. Okay. And so what I did was we took the t and we distributed it through. We took the half and we distributed through. And we got this term and this term here. Okay. All right. Let's go ahead then and simplify here. Okay. So we have v initial t here. We have 1/2 v initial t here. We can combine those two together to get us then 1/2 v final time plus 1/2 the initial time. Okay. All right. So with that said, then we can one last simplification process here. We have 1/2 in common here. We have time in common here. We can go ahead and pull those out. We have then 1/2 t v final plus v initial. Okay. All right. So at this point, let's check to make sure with this equation that we have here, does it have all the variables that we need? Let's go ahead and check that off, folks. Okay. All right. So there's v initial, okay, which is what we're solving for. Okay. V final, which is what we're given, it's right there. Time, which is what we're given, it's right there. And delta x, which is we're given, it's right there. So we have all the variables that we need in this equation right here. We have rearranged, we have combined together two of the kinematic equations to obtain an equation that we now can use that has all the variables in it. Okay. Now we're not quite done with this equation yet. We want to rearrange it because we don't want to solve for delta x here. We want to solve for v initial. And so I'm going to go ahead and write that down. I would like you to go ahead and solve for it. Okay. And I want you to be able to do it. So let's go at the top here. To solve for V initial then, let's go ahead and again, I want you to be able to do this, folks. If you can't, please make sure you come by and get that extra help. Okay? But let's go ahead. If you rearrange this equation correctly, you should end up with 2 delta x over t minus V final. And so from this equation here, we can rearrange to obtain the equation that we will need to solve for the initial. Okay. All the variables are arranged correctly. Okay. All right. So if you cannot get from this bottom equation here to this equation here, make sure you come by and see me, and let's get that done. Okay. So with that said, let's go ahead and let's plug in our variables. V initial then is going to be 2 times delta x, which is going to be 19 meters. Okay. The time interval here is going to be 4.5 seconds, minus V final here, which is going to be 7.5 meters per second. And if you notice, if you do the quick analysis, the unit analysis, this is going to end up giving you meters per second. Okay, so this is meters per second. This will be meters per second. You plug that in, folks, and you'll get your final answer then as being, I get 0.94 meters per second as your initial velocity. Okay, so not quite zero, folks. Okay, it's not quite zero, pretty close to zero, but not quite zero. Okay. All right. So, well, there it is. You know what? Mr. N's never been known for being fair. So, you know, a bit unfair to ask you this question, but like I said, I felt that you folks were up to the challenge in solving for this problem. Okay. Good news is your homework for the kinematics won't have these types of problems. Okay? I just want to make sure that you have a chance to work these out. Okay. Okay, let's go ahead then. Let's continue on. Let's continue on with the little time that I have left here, folks. I want to start talking about a free-falling object. And then hopefully next week we can go ahead and get started with the discussion on projectile motion and eventually finally get to a lab that you'll get a chance to do, the FET lab that you'll get a chance to do with the projectile motion. Okay, but we got to be able to talk about all this first before you can get that done. Okay, all right. So what is a free fall? Okay. A free fall, first of all, folks, I think as the name implies, it involves an object that is falling down towards the earth. Okay, so it's an object falling down towards the earth, and if you think about that, that object that falls moves in one direction. It's a unidirectional motion instead of moving horizontally now and moving along the x-axis. With a free fall, now we're moving along the y-axis. Okay, we're moving down. Okay, and this does. And why do we bring this up? Because we can use kinematics to describe an object that is falling. An object, whether that object is falling here on Earth, or whether the object is falling on another planet, or on any celestial body. Now, an object doesn't quite fall in space, though we could argue that there is a gravitational pull there. Anyway, that we're getting off topic there. Okay, but the free-falling object is an object that is being pulled down towards the surface of the Earth. Okay? And so if it does that, okay, the reason why we can study this and use kinematics to study an object that is falling here on Earth is because it's falling with a constant acceleration. It's falling with a constant acceleration based on the assumption then that the resistance from the air, okay, the air resistance is negligible. Okay, so that means that no resistance, no air resistance is negligible. Okay, and that's what we have to assume. Okay, we have to assume then that the resistance, the drag force, is going to be either zero or we don't include it at all. Now, in real life, we can't assume that, but here we are. Okay. We can't assume that. And the reason why, if we assume that, we can use kinematics to study a free-falling object, that is because the object that falls here, and we have Galileo here just carrying out his experiment, okay, an object that falls here down towards the Earth, okay, is going to fall at a constant acceleration. That is an acceleration that's not going to be equal to zero. It's obviously not going to be equal to zero, okay, but it's not going to change either. It's not going to change because we're ignoring air resistance. Okay? And so that acceleration is going to be constant. Okay, that means then, and if it's not zero, if it's constant and it is not zero, that means then that object continually speeds up as it reaches the ground. Okay, so if you drop something here on Earth, if you drop your pen, if you drop something, it is as it's dropping, picking up speed. Okay, it'll pick up speed and it'll continue to move faster and faster. Okay, as long as it is dropping. Now, what also is going to be, and I'm running out of time here, folks. What also is going to be true here then is any object dropped close to the surface of the Earth will have the same acceleration. Every object, okay, no matter how big or no matter how small, will always accelerate at this same rate. They may not have the same mass, but they do accelerate at the same rate. And this is something that kind of blows people's mind away. But this is an experiment that one of the Apollo spacecrafts did up in the moon. Because up in the moon there is no air, so there is no air resistance. So you can do this experiment up in the moon, or you can do this experiment in a vacuum chamber. And there's a really cool YouTube video that I came across. I'll see if I can find it and share it with you. Where in this huge vacuum chamber, okay, they carried out the experiment that was done here that Galileo proposed. Okay, and so Galileo actually studied gravity and was able to calculate for the gravitational constant. Okay, or be able to determine it using ramps, okay, using an inclined plane, but that's for a later time. Okay, and so I've run out of time here. So what we'll do then is on Tuesday we'll continue this discussion of free fall, and then I want to work out. I want to show you then how kinematics can be used to study a free falling object. Okay, all right, folks. Have a good long weekend, and I will see you folks on Tuesday.